So we're very happy to have Miranda Cheng, who is going to talk to us about going to the limit and relations between Moonshine, quantum modular forms, and so on. So Miranda, please.
Yeah. So what I'm going to do in this talk is, first of all, to go to the limit. What I meant by that is that we will consider the limiting behavior or the boundary behavior of a function on the upper plane, and when it approaches the natural boundary of the upper plane, for instance, the point at I infinity, tau going to I infinity, or q goes to 0, or tau going to some rational number and q going to root of unity. And why is that? Well, we know, and then what I will do after that is to discuss how, by going to the limit, looking at the limiting behavior, we're led to the notion of what's called quantum modular forms. And I will discuss how that notion gets related to previously discussed modular-like functions on the upper plane, and why, those functions play a role in different areas of mathematics and physics, including, for instance, Moonshine, or the counting of BPS states and vertex algebras, and so on. Right, so some motivation. Well, we know that modular forms have found a wide range of applications in many fields. And more recently, as we have heard, for instance, in a Tish talk, is that there's something else that generalizes the notion of modular form, namely the Mach modular forms. And they too have seen increasingly more and more applications in different areas, okay, including an interesting connection to finite groups that we have also heard about in other talks. And in particular, the boundary behavior of these functions near the cusps plays an important role in, for instance, how the growth of coefficients go in the context of modular forms. In, for instance, in what's known as the Carty formula, in the context of 2D CFT, and how we do the entropy computation and so on, all relies on the boundary behavior. And it also has played an important role in choosing sort of the simpler functions that display interesting connections to finite groups, as I will explain later. And we have also heard, for instance, in Sergey's talk and in Professor Hikami's talk, that how the limiting behavior gets connected to the Witten-Rashtukin invariance, or of three manifolds and other not invariants. Okay, so this consideration motivates us to consider what's called a quantum modular form, whose definition I will give in the course of talk. And this is, well, some quick explanation. Quantum modular form, you might want to know that it generalizes Mach modular form, which is itself a generalization of modular forms, right, which contains theta functions as the most simplest examples. And it also contains something else that we have also heard today, for instance, which is the so-called full theta functions, which is something that looks like theta functions, but not quite. And in particular, they are not modular, unlike the theta functions. So this is more like an overarching structure, if you wish, of these different types of functions with different properties, but they are all quantum modular forms. And in particular, we will see that on the Mach side, well, by considering the limiting behavior, we can single out like interesting Mach modular forms, that play a role in a connection to finite simple groups or finite groups in general via the so-called Moonshine connection, and how the limiting behavior plays a role here. And we will also see how full theta functions and Mach theta functions are related in some, in some concrete way via, let's say, the tau and minus tau transformation, which is a pretty exotic transformation if we're used to living in the opera plane. Okay, and this pair then they have something in common, namely such a pair will display the same behavior near the boundary of the upper half plane. And such a consideration will play an important role in the connection to three manifold and not invariant. Okay. And if time permits, but I doubt, we will also mention the connection of this between this story and the story of logarithmic vertex algebras. Okay, so I think that's my elevator pitch.